Hi students, welcome to the structural engineering lectures. The uh, the series of the finite element methods. In previous class, we have discussed about the fundamentals of finite element methods, wherein we have seen the 2D four-node quadrilateral students. Right. In today's class, we shall see the discussions on numerical integration techniques, Gaussian quadrature, right? And as Gaussian quadratures, right? Now, let us move to the discussions. Right? This is how the Gaussian quadrature of numerical integration. In previous class or in previous video, we have seen that we have derived the element stiffness matrix, which was given by the integration of double integration over area b transpose db dv, where dv is equal to thickness of that four node quadrilateral multiplied by its area. That area dA within double integration dA, or the dA was replaced with that j d dj that d dxi d eta. Hence the uh, integration of this will give 64 coefficients. Actually, there is a double integration that was 2D 4 node quadrilateral students. Therefore, it was having 8 degrees of freedoms. Hence, the size of the element stiffness matrix was 8 by 8, 64 coefficients. Right? Therefore, I need to do 64 calculations using double integration of mathematics rules of integration, right? However, practically obtaining these results by mathematical integrations is a very tedious job. Therefore, we'll be using as an equivalent to that, we'll be using the Gaussian quadrature technique or Gaussian quadrature approach of numerical integration for getting an approximate solution for arriving at those coefficients. Right? Wherever we require single integration or double integration, we'll be using this numerical integrations rather than that of the real mathematical integration. That is what I hope students you understood why we require a Gaussian quadrature of numerical integration. Then if you understood, let us move to the application of this to one-dimensional problems. This application of numerical integration to one-dimensional problems, students. Right? Then that is how for one-dimensional problems, I have an integral notated by capital I is given by -1 to +1 f of xi dxi. Let it be equation 1 using endpoint formula. Now what I can write, this integral is approximately equal to w1 multiplied by f of xi1 plus w2 multiplied by f of xi2 plus w3 f of xi3, so on and so forth up to wn f of xin using endpoint formula, right? Then that is how that integral on the left hand side -1 to +1 f of xi dxi is approximately equal to, I am saying approximately. However, that approximation can be improved at any given point of time. Right? Therefore, that is our w1 f of xi1 plus w2 f of xi2, so on and so forth, wn f of xin. Let it be given by equation 2, students, where w1, w2 dash dash up to wn are the weightage factors or weighting functions, which are similar to that of the shape function, but these are not shape function, students. Right? These are the weightages, right, or weightages values, right? And xi1, xi2 dash dash up to xin are the sample points or sampling points, or these are called Gaussian points. Right? Now this is how the integral of one-dimensional problem, because we are there in one-dimensional problem, -1 to +1 f of xi dxi can be evaluated using endpoint formula. Now let us see If I take only one, n is equal to 1, then that will become a 1-point formula, students. Then I is equal to minus 1 to plus 1 f of z dxi is approximately equal to, then I'll take only the very first term of that n-point formula as w1 multiplied by f of xi1. Let it be given by equation 3. Then I do have w1 is one parameter as well as f of xi1, means xi1 is another parameter. Therefore, until unless I know what are these w1 and xi1, I cannot get a solution for this integral. Using numerical integration. Please make a note that we are not doing any integration, students. I am not doing any practical integration as we used to do in mathematics. I am just substituting weighting function value and I am weightage factor multiplied by that function value at a sampling point xi1, xi2 dash dash, right? Using so many number of points, right? Hence, in 1-point formula, I will substitute only the very first sampling point xi1. F of xi1, I'll get that value of that function multiplied by weightage w1 or weighting factor or weightage factor w1, right? Let it be equation 3. However, I do have two parameters unknown. Therefore, I need to evaluate these. Therefore, now I'll assume the function f of xi. Actually, there is an integral which is integral over minus 1 to plus 1 f of xi dxi is an integral where the function is f of xi, which is now assumed as a0 plus a1 xi. Let it be equation 4. Then I'll substitute this in the above equation. Then that becomes minus 1 to plus 1 f of xi dxi is equal to minus 1 to plus 1 a0 plus a1 xi dxi. Please make a note that I do have two unknown parameters w1 as well as xi1. Hence, I am using two constants a0 a1 and I do have two parameters. Therefore, 2 minus 1, the order of the polynomial here is 1. Therefore, if the order of the polynomial is 1, then only two constants will be there, right? That is two parameters. If I decide what is a0 a1, I can get this function value, but in numerical integration will not get the values of a0 and a1, students. Indeed, I'll get what is the value of the sampling point xi1 and also what is the value of w1. That now I'll evaluate. Right? Therefore, by substituting this in the above equation, now I'll get this LHS integral is equal to RHS minus 1 to plus 1 a0 a1 xi dxi. Therefore, if I integrate, now I'll get a0 xi plus a1 xi square by 2 minus 1 to plus 1, or substituting lower bound and upper bound, students, I'll get I is equal to 2a0 plus a2 by a1 by 2, 1 minus 1, this gets cancelled. Therefore, leading to 2a0 integral is equal to 2a0. Let it be equation 5. Then I know already that integral, which is now 2a01, which is evaluated as 2a01, right, is my integral in terms of Gaussian quadrature, numerical integration as w1 f of xi1. Therefore, I'll equate one with the other, and I'll also substitute what is xi1 in the given function, which is assumed function as a0 plus a1 xi. Therefore, now xi takes a value of xi1, students. Then that is how the right hand side will become w1 multiplied by a0 plus a1 xi1 is equal to 2a0. Now I'll expand the terms and I'll see what are the terms with a0 and what are the terms with a1. That is how w1 a0 plus w1 xi1 multiplied by a1 is equal to 2a0. Now I'll compare on either side LHS with RHS the terms, the coefficients of these a0 terms, right? On the left hand side I do have 2, on the right hand side w1. Therefore, comparing with, now I'll get w1 is equal to 2, and similarly I can say that w1 is not there on the a1 is not there on the left hand side. Therefore, xi1 multiplied by W1, xi1 multiplied by W1 must be equal to 0. But already we decided from the first condition that W1 must be equal to 2, comparing LHS with RHS. Therefore, W1 cannot be 0. Then, however, the product of W1 multiplied by xi1 must be equal to 0 from LHS to RHS, right? Therefore, we can say that xi1 must be equal to 0. Means the sampling point is at the CG of that given element, at the CG of this given element. That is how 1D 2 node or 1D 3 node element as appropriate at the CG, right? Then I'll now substitute this in the above equation, right? Now I'll try to get what is the error, right? That is how the error is minus 1 to plus 1 a0 plus a1 xi multiplied by d xi is actual value using the actual mathematics rule. But however, I'm getting this result using numerical integration as w1 multiplied by f of xi1, right? This is using numerical integration. This is using the mathematics integration procedures, right? Therefore, now my aim or our aim is to minimize the error, students. Therefore, now I can say that this error is equal to 0. Error is equal to 0. Then I'll integrate and substitute the lower bound and upper bound in this function. Then it will become a0 xi plus a1 xi square by 2 minus 1 to plus 1 minus w1 f of xi1. And upon substitution of lower bound and upper bound, now I'll get a0 multiplied by 2, a1 by 2 multiplied by 0 minus w a0 plus a1 xi1 is equal to 0. I'll take the terms with a0, students. Then that is how a0 is with 2 minus w1 multiplied by a0, and also I'll take the terms with a1. Here a1 multiplied by 0, it will not contribute. What is there only is w1 multiplied by xi1 with a1. This is equal to 0 because we want to minimize the error. If error is equal to 0, then I'll get exact solution. However, we also know that a0 and a1 cannot be 0. If a0 and a1 they themselves are 0, then the function will become 0. Means there is no solution for that integral. Therefore, they can never be 0, students. Hence, what can be 0? Their coefficients must be equal to 0. Hence, I'll say 2 minus w1 must be equal to 0, right? As well as w1 multiplied by xi1. w1 multiplied by xi1 is equal to 0. Therefore, doing which now I'll get w1 must be equal to 2. But already w1 is equal to 2. Therefore, now substitute in the next equation that 2 multiplied by 2 multiplied by xi1. 2 multiplied by xi1 is equal to 0. Therefore, that gives that xi1 must be equal to 0. That is how I have evaluated what is the weightage. W1 is equal to 2 and sampling point is at mid node. Let us say this is 2 noded 1D element. Then I need to take the sampling point at mid xi1. Here xi1 is equal to 0. Its weightage is equal to 2. Right? Then now if I substitute these, then I'll get the result as 2 multiplied by f of xi1 as the integral value, as we have seen in the definition. Right? Now, if you understood that, then we'll move to the next subheading as a 2-point formula, students. Right? Where I'll take n is equal to 2, then that integral is now I is equal to minus 1 to plus 1 f of xi dxi is equal to w1 f of xi1 plus w2 multiplied by f of xi2, that integral by taking two terms. But I want to write what are the polynomials and what are the coefficients. Therefore, I do have now w1 w2 two weightages or weightage factors, and as well as two unknown sampling points xi1 and xi2. Therefore, in turn, I do have 4 unknown parameters here. 4 unknown parameters here, students. Therefore, I must take a function f of xi having four constants a naught, a1, a2, a3 or 4 minus 1 cubic cubic polynomial, right? That is how I am proposing the function f of xi given by this a naught plus a1 xi plus a2 xi square plus a3 xi cubed, a3 xi cubed. If I want to find the error, then I'll do this. That is how the error is defined by minus 1 to plus 1 f of xi d xi using the mathematics fundamentals, but I am finding out its result using numerical integration as w1 f of xi1 plus w2 f of xi2. Therefore that difference of these two results must be equal to 0 for exact solution, right? For exact solution, that difference must be equal to 0. Therefore now I'll bring that function and I'll substitute minus 1 to plus 1. That is how this becomes 2a0 plus 2a2 by 3, right? Then w multiplied by f of xi1. This is what f of xi1, students. W1 multiplied by a0 plus a1 xi1, a2 xi1 square, a3 xi1 cubed. Similarly, w2 multiplied by f of xi2. w2 multiplied by f of xi2 is a0 plus a1 xi2 plus a2 xi2 square, a3 xi2 cubed, right? That is how the error. Now what I'll do is I'll take all the terms containing this a0 as 2 minus w1 minus w2 multiplied by a0, right? Then all the terms containing a1, right, as minus w1 xi1 plus w2 xi2 multiplied by a1. Similarly, I'll take the terms with a2 as 2 by 3 minus w1 xi1 square minus w2 xi2 square multiplied by a2, and I'll take the terms with a3 as w1 xi1 cubed plus w2 xi2 cubed, that multiplied by minus a3 must be equal to 0. Right hand side must be equal to 0, students, because I want an exact solution, right? And so I do have a0, a1, a2, a3, four unknown constants. However, these unknown constants a1, a2, a3, a1, a0, a1, a2, a3 cannot be 0, because if they are 0, then the function ceases. The function does not exist. Therefore, they cannot be 0. Therefore, their coefficients can be 0. Therefore, using that, now I'll say that yes, this is all right. Their coefficients, 4 equations. I do have first equation as 2 minus w1 minus w2 must be equal to 0, right? That gives a w1 plus w2 must be equal to 2, right? And actually that is equal to 2, right? Then the second equation is w1 multiplied by xi1 plus w2 multiplied by xi2 must be equal to 0. The second equation, right, having linear polynomials in terms of xi1, right, and having the quadratic polynomials, right, like this 2 by 3. The coefficient of this a2, I'm just recalling that as 2 by 3 w1 xi1 square minus w2 xi2 square, that must be equal to 0, because a2 cannot be 0. That is how the third equation as w1 xi1 square plus w2 xi2 square must be equal to 2 by 3, and that of the a3 as w1 multiplied by xi1 cubed plus w2 multiplied by xi2 cubed must be equal to 0. Therefore, I do have 4 parameters as w1, w2 as well as xi1 and xi2. Therefore, I do have 4 equations, students. I do have 4 unknown parameters w1, w2 and xi1, xi2. I do have 4. These are 4 simultaneous complex equations. 4 simultaneous complex equations. This is not just linear nor quadratic, right? I do have cubic variation, students, right? That is how one equation says that in terms of w1, w2, right? Even in terms of linear polynomials, quadratic polynomials and cubic polynomials. Therefore, this is a complexes, 4 simultaneous equations. Therefore, its solution is unique, right? solving these four simultaneous complex equations, I do have only a unique solution, that these four equations will be satisfied only if and if W1 is equal to 1, W2 is equal to 1, right, 1 unity, and Xi1 is equal to minus 1 by root 3, right, Xi2 is equal to plus 1 by root 3. That is only if these four values are substituted in the above four equations, then only all the four simultaneous equations, complex simultaneous equations are satisfied, right. Then that is how now I am showing that is a two noded one-dimensional element, that is a first node and the second node. Now the first node is at Xi is equal to minus 1, the second node is at Xi is equal to plus 1, right, plus 1. Then in this numerical integration, we are taking W1 is equal to 1 at Xi is equal to minus 1 by root 3. Xi is equal to minus 1 by root 3. That is equal to minus 0.5773. Right. Similarly, W2 is equal to 1 at the sampling point, where that position of the sampling point along the Xi axis, local Cartesian local coordinate system, or Xi eta space, or Xi space here, right? Xi space here, right? Is W2 is equal to 1 at Xi2 plus 0.5773, or 1 by root 3. That is how the sampling points Xi1 and Xi2, their numeric values are derived, right? This is the CG of this element, students. At the midpoint, I do have the CG, right, where Xi is equal to 0. Then by substituting this, then you will get the result using numerical integration. Now, if you understood that, students, then we'll move to the 3-point formula, where n is equal to 3. Then there is that integral I is equal to minus 1 to plus 1 f of xi dxi, students, is approximately equal to w1 f of xi1 plus w2 f of xi2 w3 multiplied by f of xi3. I do have n is equal to 3, means 3 weightage functions w1, w2, w3, and 3 sampling points xi1, xi2, xi3. Therefore, in turn, I do have 6 unknown parameters in total as w1 to w3, xi1 to xi3. Therefore, as I do have 6 unknown parameters, students, then I'll propose the shape functions having 6 constants, 6 minus 1. Therefore, the order of the polynomial xi is fifth order, right? That is how f of xi, I am proposing f of xi is equal to a0 plus a1 xi plus a2 xi square, a3 xi cubed plus a4 xi to the power 4 plus a5 z to the power 5. Therefore, in total, it has 6 constants and fifth order polynomial function is proposed, right? Therefore, doing in a similar fashion as we have discussed, you just our aim is to get this integral f of xi dxi minus 1 to plus 1 exact value, but I'll not get that exact value. Therefore, what I'll do is I'll write the error I is equal to f of xi dxi minus 1 to plus 1 minus w1 f of xi1 minus w2 f of xi2 minus w3 f of xi3. Now, as you have discussed in the previous one point formula as 2-point formula, now you write the equations. Now you will get 6 simultaneous equations, students. We have seen in 1-point formula, right, 2 simultaneous equations. In 2-point formula, we have 4 simultaneous equations. Now I'll get like that 6 simultaneous equations, solving which now you will get these 6 unknown parameters as w1 is equal to w3 is equal to 0.5555, right? Actually, it is infinite series, but let us restrict it to 4 or 8 digits, right, or decimals, or 8 decimals, sorry, right? Similarly, w2 must be equal to 0.8888, right? That is how the weightage of values at the sampling points of xi1 is equal to minus 0.7746 and xi2 is equal to 0 at the mid node or at the CG of this element, and xi3 on the positive side as plus 0.7746, plus 0.7746, right? That is how it is shown schematically here, students, right? That is how W1 having a weightage of 0.5555 at sampling point of minus 0.7746. W2 is having a weightage of 0, but at a weightage of, a weightage of 0.8888 at sampling point of xi2 is equal to 0, and this W3 is having a weightage of 0.5555 at a sampling point of 0.7746 plus value. By substituting this, you will get the exact an approximate value for that integral. All these are the approximations only, right? Numerical integration will give an approximate solution, not exact solution. However, that approximation can be improved by taking, if you are not getting in 1 point formula, then you take 2 point formula. If not, if you are having still error, you take 3 point formula, or next fourth or dash dash dash, or you increase the number of sampling points so that you will get the result tending towards the exact result as obtained from the mathematics fundamentals. Now let us see as an example how this numerical integration can help in arriving at the integral values, right? Now I'm taking this example, students, right? Evaluate the integral I using 1 point as well as 2 point formulas of Gauss quadrature rule, Gauss quadrature integration techniques, right? That is how I is equal to minus 1 to plus 1 3 e to the power x plus x square plus 1 by x plus 2 dx, right? Here either I can say this x, or the integral may be minus 1 to plus 1 3 e to the power xi square plus 1 by xi plus 2 dxi. Therefore here it is immaterial for this integration. If it is the function is in terms of x, then dx. If the function is in terms of xi, then this is dxi. Therefore that is how that limits of xi minus 1 to plus 1. Generally in local coordinate system, I do have the lower bound and upper bound as minus 1 to plus 1, lower bound and upper bound as minus 1 to plus 1, right? Then let us use the 1 point formula, right? We do have this integral minus 1 to plus 1 3 to the power x plus x square plus 1 plus 1 by x plus 2 dx, right? Using the mathematical integration rule, now I can say that this is 3 e to the power x plus x cube by 3 log to the base e x plus 2 minus 1 to plus 1. By substituting lower bound and upper bound, now I'll get this, right? Then finally I'll get the result as 3e minus 3 by e plus 2 by 3 log 3 to the base e, or its result is 8.816 up to the third decimal, students, right? Then that is what exact solution using the mathematics integration rules. Therefore for evaluating that, you should be aware of the mathematics integration formulae also, but that is a tedious process. Remembering all those formulae and right substituting and evaluating is a tedious process. Therefore indeed we'll use here the numerical integration, right, using 1 point formula. Then for 1 point formula, we know that weightage factor or weightage W1 is equal to 2, and the sampling point xi1, or here it is x1, is equal to 0. Therefore I is equal to W1 f of xi1. This is approximately equal to, students, not exactly, right? Hence W1 is equal to 2 f of sampling point, either xi1 or x1 is, I need to evaluate at the CG where xi1 is equal to 0. Therefore substituting that 0 in that function, now I'll get 3 to the power 0 plus 1 by 2. That now becomes 2 multiplied by 3.5 is equal to 7. Now you please see that there is a lot of difference between that exact solution 8.816 to that of 7. Therefore how much is the error? Error is 1.816 compared to that of the exact result. This is approximately 20% error, students, right? Therefore I told that this is approximate solution only. However, if you are not satisfied with this much of error, then what you can do is that you can find by increasing to another point, 2 point, right? 2 point formula, 2 point Gauss quadrature formula. As now, that is how that using 2 point I can say that I is given by approximately equal to, once again, as w1 f of xi1 plus w2 multiplied by f of xi2, where w1 w2 weightages are 1 and 1, and the sampling points xi1 is equal to minus 1 by root 3 and xi2 is equal to plus 1 by root 3. Here they are respectively x1 and x2. Therefore integral I is f of x1 plus f of x2, means whereas that weightage is equal to 1 multiplied by f of x1, 1 multiplied by f of x2. Therefore now it becomes the function of minus 1 by root 3 plus function of 1 by root 3. That's it, right? Therefore substituting that 1 by root 3 wherever x is there, substituting 1 minus 1 by root 3 and plus 1 by root 3 in the function and taking its summation, now I'll get the result as 8.785 using 2 point formula. Whereas using exact mathematical integration rule, I'll get 8.816. Hence the error is hardly, there is a small error, student. Now you can see that error is 0.0303, right? Compared to that of 8.816, that is hardly 0.34% error, which is very small, negligible. It can be neglected also. That is how from 1 point formula, the one point formula where the error was 1.816, where the error was 20%, we have reached just by increasing another point, hardly 0.34% error, right? If you are still not satisfied with this 0.34% accuracy, then you can use 3 point formula. Then we can say that I is approximately equal to w1 f of x1, w2 f of x2, w3 f of x3, where the sampling points x1 is minus 0.7746, x2 0, x3 is equal to 0.7746, and the weightages are w1, w2 both 0.5555 and w2 is 0.8888. If you substitute that, then even you will get now very improved value. Even the error may be, I don't know, that that error is almost tending towards 0 now. That is how you can improve the further accuracy of the integral, right? Now if you understood that, students, now let us apply this Gauss quadrature numerical integration concepts to 2D problems, right? That is how integral minus 1 to plus 1, minus 1 to plus 1 f of xi eta d xi d eta. We are there in 2D problems, therefore xi eta, two are there like this, xi eta, right? Therefore it is approximately equal to minus I is equal to minus 1 to n, j is equal to I is equal to 1 to n summation j is equal to summation j is equal to 1 to m wj multiplied by f of xi eta j. Let it be given by equation 6, where wi wj and xi eta j are the weightages, w1 wi wj are the weightages, and xi eta j are the sampling points. Now we'll use the 2 by 2 rule, students, right? Wherein I'll take that 1 2 3 4 noded quadrilateral, now I'll take the sampling points, right? That is how, right? 1 2 3 4, within this I'll take 1 2 3 4, right? Then however for this now I'll take any one of the direction, therefore now let us say I'm taking the z direction, students. Then I can say that this is sample point 1 and sample point 2, and this is how that CG xi is equal to 0 and xi is equal to plus 1 in the positive x direction, positive z direction. In the negative z direction, xi is equal to minus 1, right? Then these are the two sampling points, xi1 and xi2, right? where xi1 is a mirror image of xi2 on the negative side, right? That is how the sampling point 1 and 2 and 3 and 4 respectively along xi direction. Similarly, the sampling points 2 and 3 and 1 and 4 are along eta direction, right? Eta direction respectively. Therefore, these sampling points, the lines passing through these sampling points 1 and 2, 4 and 3 along z direction parallel to xi, as well as connecting between 1 and 4 and 2 and 3 are if they are interconnected, they will meet at these 4 sampling points, which are called Gaussian points. 1 2 3 4, 1 2 3 4. Their values, as we already seen in 1D 2-point formula, 1D Gaussian quadrature using 2-point formula that just we have already proved in the previous subheadings, that sampling point must be xi is equal to minus 1 by root 3 and xi2 is equal to plus 1 by root 3. Similarly, if I take the eta direction, that eta must be at minus 1 by root 3, another eta 2 must be equal to plus 1 by root 3. That is how along xi direction, right? Xi1, xi2 along eta direction, eta 1, eta 2, right? Then that is how I'll call this as 2 by 2 rule. I'll call this as 2 by 2 rule, students, right? Like this, right? That is how 2 by 2, right? That is how xi is equal to minus 1 by root 3, xi2 is equal to plus 1 by root 3, eta is equal to minus 1 by root 3, eta 2 is equal to plus 1 by root 3, right? Plus 1 by root 3. Then that is how my integral is given by minus 1 to plus 1 f of xi eta dxi d eta. Then I can write that is approximately equal to, right, w1 square f of xi1 eta 1, w2 w1 f of xi2 eta 2. Now please see that if I am substituting xi2, then I do have weightage w2, right? Now I am substituting here 2. Therefore w2 square f of xi2 eta 2 plus w1 w2 f of xi1 eta 2 using 2 by 2 Gaussian quadrature rule as applicable to the 2D analysis. This is applicable for 2D analysis students, right? 2D problems, right? Then that is how my integral we have seen just now. Let it be given by the seventh equation, right? Then now I can evaluate what are these w1 w2 xi1 xi2, right? xi1 xi2, right? Therefore that is how I can prove that xi1 is equal to minus 1 by root 3, xi2 plus 1 by root 3 with weightage of w1 is equal to 1, w2 is equal to 1, right? And sorry student, with weightage of w1 is equal to 1, w2 is equal to 1, as we have seen like this, right? And xi1 is equal to minus 1 by root 3, xi2 is equal to plus 1 by root 3, right? Similarly, along eta direction, I do have I can prove that eta 1 must be equal to minus 1 by root 3, eta 2 is equal to plus 1 by root 3 with weightages of w1 w2 once again as 1 1. If I substitute all those, then I'll get the integral value. Without doing actual integration, I'll get approximate solution using numerical integration of Gaussian quadrature using 2 by 2 rule as applicable to 2D analysis or 2D elements, right? Now why we require these students like this, right? w1 is equal to w2 is equal to 1 minus xi1 is equal to xi2 is equal to plus 1 by root 3 minus eta 1 is equal to eta 2 is equal to plus 1 by root 3. That why next question is why we require this integration. That I already told that in the very first discussion, as element shiftness matrix is given by for 2D 4-node quadrilateral given by t minus 1 to plus 1 minus 1 to plus 1 B transpose D B det J d xi d eta. But however, we have already seen that B is not a constant matrix that varies linearly with the polynomials of xi and eta. And D is a material property matrix. It can be taken out of integration, but I can't take it out because B is a matrix operated upon a matrix operated upon once again a matrix having xi and eta terms that multiplied by det j, right? Hence, after matrix multiplication of these matrices in terms of polynomial xi and eta, you evaluate each and every term from -1 to +1, -1 to +1 in real integration, but that is not practically feasible, students. For we have seen for 2D 4-node quadrilateral itself, I do have 64 coefficients because 8 degrees of freedom, 8 by 8, 24, 8 by 8, 64. Even if I take the symmetry, at least more than half of the coefficients I need to evaluate. Therefore, that is not practically feasible, in which case we'll use only Gauss quadrature approach of numerical integration given by this I is equal to -1 to +1, -1 to +1 f of xi eta d xi d eta, right? Therefore, comparing this, now I can say that my function f of xi eta is t b transpose d b det j, right? The rest of the thing is d xi d eta. That is how my function, right? Therefore, that is my integral, right? Then I can that is my integral actually. Then I can evaluate the coefficients of these stiffness kij, means k11, k12 dash 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 up to k1n, so on and so forth up to knn using this numerical integration as w1 square f of xi1 eta 1, w1 w2 f of xi1 eta 2, w2 w1 f of xi2 eta 1, w2 square f of xi2 eta 2, right? That is how it will give without doing any numerical integration. Students, I hope you understood this discussion then. Okay, students, we have discussed in today's class the numerical integrations, Gaussian quadratures. In the next class, we shall discuss 2D higher order isoparametric elements like this, right? Therefore, if you like these lectures on finite element methods as well as the structure engineering lectures, please do click like, share and subscribe to our YouTube channel, students, right? We'll meet once again with another discussion on the finite element methods. Till then, bye bye, students, right?